The oil and gas industry is one of the biggest wasters of water in the state of New Mexico. Through their processes, including hydraulic fracturing, they produce 5.4 million gallons of produced water per day, according to the New Mexico Energy, Minerals, and Natural Resources Department. Produced water is the highly contaminated water produced in the oil and gas extraction process. The vast majority of this water is injected deep underground, where it is forgotten about. Meanwhile, the state of New Mexico is in a water crisis, one that is only getting worse as climate change advances. Scientists say that without action, in 50 years, New Mexico will have a shortage of 750,000 acre-feet of water. The current methods of wastewater treatment do not work on the highly contaminated and chemically complex produced water, but research is being conducted on methods that could. One of these methods is membrane distillation.
In membrane distillation, we're using what we think of as a hydrophobic or a so-called water-fearing membrane to support an air gap. And that air gap separates a warmer, contaminated feed stream from a cooler, pure product water. So the hydrophobicity of the membrane is key in preventing contaminants. So it acts kind of like your raincoat or your waterproof hiking boots in that it allows air and therefore water vapor to get through, but it prevents liquid water and all the contaminants associated with liquid water from getting through. So if we can prevent liquid water and extract only pure water vapor, we can separate pure water from things like salts, from heavy metals, from radioactive materials, from microorganisms, from any contaminant that isn't volatile. So fouling is often called the Achilles heel or the weak point of membrane processes. So fouling is basically just the accumulation of stuff on the membrane surface. So it can be anything from microorganisms to particles to salt crystals. And if those accumulate on the surface, they can block membrane pores. And that prevents water from getting through, whether it's in the liquid phase or what we want it to be, right, in the vapor phase. So as that fouling layer develops, we have to provide more and more energy in order to keep passing water through the membrane. And wetting is kind of a fun one because it's unique to membrane distillation. So as I mentioned, in membrane distillation, we need this hydrophobic membrane to support that air gap. If that air gap closes, or if liquid water gets through the membrane, then it can bring all the contaminants associated with that liquid water with it. So if you imagine a liquid feed stream that contains salts, that contains microorganisms, that contains heavy metals, if that liquid gets through and mixes with our pure water, it's going to contaminate that water. So fouling is basically caused by any foulant that might be in your feed stream. So suspended sediments or soils in your water, that could be microorganisms, that could be salt crystals if we're dealing with high salinities, where salts are precipitating out of solution and then crystallizing on the membrane surface. And wetting can also be caused by a few different things. So if we apply too much hydraulic pressure to the water, that can force liquid water into the pore space, kind of overcoming the wetting resistance of our membrane. But we can also have wetting happen due to fouling. So if you imagine something like a salt crystal forming on the membrane surface, that salt crystal is very hydrophilic. It likes to be wet. So that can draw liquid water into the membrane pore space and then kind of pull water through. So there are some challenges with making membrane distillation commercially viable, which is probably why it's not widely commercially used yet, right? So one major challenge is membranes themselves. So right now there's only a couple of companies that are producing commercial MD membranes. And the second challenge I'll mention is, there's just not enough data yet at big scales. So we've done a lot of research, our group and other groups, at the bench scale, so kind of dealing with small membranes in the lab, but doing research at pilot scale, out in the field with real waters for longer times, will give us a lot more information about how this process works. So you may have heard of reverse osmosis, or RO. So reverse osmosis is our current state of the art for desalination, for separating pure water from salty water streams. So in reverse osmosis, it's a pressure-driven process. So we're applying high pressure to that feed stream, that saline or that contaminated water stream, and we're just pushing pure water through a dense membrane, a membrane that rejects salt. So it's going to allow pure water molecules to pass through, and it's going to reject salt ions. But the more salt we have in our water, the harder we have to push, the higher the pressure we have to apply. And that means that it gets a lot more energy intensive and also more expensive and just practically challenging to do reverse osmosis for saltier, more concentrated brines. Right now, the operating limit is about 2 times that of seawater. So when we're dealing with wastewaters that are more concentrated than that, including produced water from the oil and gas industry, we have to consider processes that aren't pressure-driven, things like membrane distillation, which is thermally driven. So as I mentioned before, One of the key challenges in membrane distillation is getting membranes. So previous researchers have started to look at ways to design better membranes, but there's not enough understanding yet of how membrane properties drive performance for complex feed streams. So what happens when you not only have a lot of salt, but you have a lot of different types of salts? What happens when you also have phthalates present as well as salts? But the goal of this project is really to design a new MD membrane that allows us to achieve produced water desalination, to allow us to produce clean water from produced water waste streams. We can also think, of all kinds of challenging wastewaters that we can treat. So if we can design separation processes that allow us to do that, that would be a huge advancement.
Thanks for watching. I hope you learned a little bit about membrane distillation, a technology that could help propel us into a more sustainable future.